Hi, I'm Joe Suck, and this is Self-Tuning Bandits over Unknown Covariate-Shifts, which is joint work with Samory Kpotufe at Columbia. So our setup is stochastic contextual bandits, where at each time or round t, an agent observes a context xt and uses xt and past decisions and observations to select an action or arm among k available arms. The agent then observes a reward for the selected action. The goal here, of course, is to maximize the earned reward. Here, we consider a non-stationary environment in which the distribution of context x is changing over time from p1x to p2x, terminating at a distribution qx. Here, each of the p's and the q represent the joint distribution of the context x and reward y at a particular phase, so that the px's and qx are the corresponding context marginal distributions. The Bandits agent plays a stationary phase under each of these distributions in the shown consecutive order. We then want to do as well as possible with respect to any stationary distribution Q under this general setup. Now, prior works on non-stationary bandits treat the shifts in distribution as adversarial in nature, meaning earlier observations under P can be potentially harmful to performance under Q. And their algorithmic design is thus to minimize such harm by possibly ignoring earlier observations. However, the world is not that adversarial. For example, we may consider running a clinical trial using contextual bandits, where the context could be a patient's biometric information, say, and the actions are the available treatments in the trial, and the rewards are the treatment outcomes. Here, while we might expect the makeup of biometrics in the population to change over time, a particular individual's biometrics should remain just as predictive of their treatment outcomes in the present as it was in the past. Along this line of thinking, we consider one type of shift which captures that example, formally called Covariate-Shift, which is the most common type of distribution shift studied in transfer learning literature. In Covariate-Shift, we have that the distribution of the rewards given a particular context are fixed over time, while the distribution of context can change, just as in the example of the clinical trial. Then the main questions we would like to answer are: what is the best possible performance under the stationary phase of distribution Q, and how does it depend on past distributions? Secondly, which algorithms achieve this performance? To answer the first question, we first need to quantify the utility of past observations to current performance under Q. And under covariate shift in particular, we need only focus on the shift of the context, px and to qx. Intuitively, the usefulness of past experience will depend on whether large or probable regions of the context space under Q were observed in the past. Let's look at these two examples of the context space with just these two distributions, px and qx, colored here in pink and blue. On the left, we see that experience under P is helpful for Q since the support of px has good coverage of the support of qx. In other words, experience under P contributes useful information about the reward values under Q. Meanwhile, on the right picture, we see that the support of px fails to cover large regions of the support of qx. And so if we observe new context points under Q in the non-overlapping area, then we wouldn't expect earlier context from P to be of any use to us. So we'd like to capture a continuum of both regimes, and so we formalize the distance between P and Q using the notion of transfer exponent from earlier work on classification. The transfer exponent, gamma, captures the extent to which px has sufficient mass in regions of large mass under qx. As an example, when qx has mass outside of px's support, as in the right picture above, we have that gamma is equal to infinity, which is the largest possible discrepancy. While on the other hand, gamma equals 0 represents the most benign shifts in context distribution. Gamma can also capture a change in the effective dimension of the support, as we see in the left picture, where the support of the context goes from 2 dimensions to 1 dimension. Next, the utility of P also depends on how long we played under P. Looking at the left picture again, although P has good coverage of Q, if we had only played, say, 3 rounds under distribution P, then the experience under P might not be of much use to Q, since we likely did not observe points in the support of Q. On the other hand, if we had played a large number of rounds under P, then we would have more knowledge about Q. Next, we discuss the general algorithmic strategy and the challenges of this setting. Our main assumption is a nonparametric one, that of Lipschitz expected rewards as a function denoted fi for arm I of the context, where, as in many works on nonparametric bandits, we assume the context lie in a unit hypercube. A common strategy in this setting, which we also follow, is to then partition the context space and eliminate or rule out suboptimal arms locally in individual cells of the partition. And we do this by estimating each fi within a cell using nearby context. The key algorithmic question here is then one of model selection. How refined of a partition should we choose, or what resolution should the partition be at? We can see right away that there is statistical difficulty in selecting the optimal refinement. For instance, if we select a resolution too small, then the cell containing our current context might not have enough points to accurately estimate the mean rewards. On the other hand, selecting a resolution too large might allow far-away observations to bias our reward estimates. Here, we can describe the various refinements with a tree, where each node is a cell of a particular partition, and each level or depth, as colored in red here, represents a partition at a particular resolution. For example, 1, 1/2, or 1/4. The task of model selection, as said before, can then now be phrased in terms of selecting the right level of our tree. However, the crucial and novel difficulty here is that the optimal level turns out to depend on unknown distributional parameters, such as the dimensions of the context distributions and the times of the shifts. In particular, it depends on said parameters for all previously seen distributions up to that point. To counter this, we propose an adaptive strategy. Now, past works in the stationary setting chose a global level, meaning that they used a fixed level of the tree or fixed partition of the context space at each round, but they did so assuming distributional knowledge, which we will not do here. Instead, at each round t, we make a local choice of the level, which depends on the observed context, xt, at that round. In particular, we consider the path in the tree from the root node through nodes containing xt. This path represents all the cells at various refinements containing our observed context. And we use this path to then select the local choice of level R as that which balances regression bias and variance, or such that R is approximately 1 over the square root of the number of contexts observed in that cell so far, denoted nrxt. Now, this selection method introduces some technical bookkeeping issues. Namely, we would like the number of times we've observed context in a cell, nrxt here, to be about the same as the number of reward observations for a given arm. But in bandit feedback, these quantities differ since we only observe the reward of an arm when we pull it. So to make matters more complicated, we might change the choice of level R, which is now a random quantity, between rounds because we are choosing it adaptively. And this is going to make it difficult to ensure that each arm has been pulled the right number of times in a given cell. And so much of the analysis is devoted to resolving these issues and can be found in the paper. This adaptive choice of level, however, yields regret rates which are adaptive to all parameters. And so this will be our main result. Now, recall that our setup has shifts in the context. So suppose P1 through PM and then Q are the distributions observed in this order, so that we play under P1 for N1 rounds, then P2 for N2 rounds, and so on, for a total of NP rounds under the stationary phases P1 through PM. And then we play under distribution Q for NQ rounds. Now suppose each of the PJs has a context marginal, PJX, which with transfer exponent gamma j, which, just going back to earlier intuition, just plainly means that gamma j measures the extent to which Px contributes mass to Qx. Then our main result is a regret upper bound on the last stationary phase under Q, or the last NQ rounds played. Now here, our regret bound depends on the distributional parameters of all the past distributions, but it also depends on two distributional parameters of Q. First, there's the effective or intrinsic dimension, little d, of Qx, which we allow to be unknown and potentially much smaller than the ambient dimension of the context space, which is a departure from earlier works. Second, alpha is a margin parameter which captures low noise in the gaps of arm rewards. This is just a commonly considered parameter in this line of work. And the exponent phi here is a function of all the parameters, and we avoid defining it for the sake of presentation. Now, np to the phi, the term inside the regret bound, can be considered the effective amount of past experience contributed to Q by the past distributions, P1 through PM. And in particular, it captures the degree to which we can benefit from the past. In particular, right away, we see that this regret bound is always smaller than the optimal stationary regret, regardless of the parameter values. In other words, our algorithm never does worse than an optimal stationary procedure, which ignores all previous distributions. Next, these regret rates are, in fact, tight up to log terms, and thus nearly minimax optimal. Lastly, here, this result is of interest even in the stationary case, since we didn't actually assume that our context marginals are nearly uniform or satisfy nearly uniform assumptions, which is standard in all prior works on nonparametric contextual bandits. And it's worth noting here that this is a difficult setting, even in the stationary case, as going back to the problem of level selection in our trees, the correct choice of level turns out to be different in this setting than in the nearly uniform case. Hence, the methods of earlier works would not have worked for the generalized setting, even with no shifts in the context. So recall, our main two questions were, what is the best possible performance under Q, and how does it depend on past distributions? And secondly, which algorithms achieve this? Our results show that we've captured how useful previous distributions are and propose an algorithm that can achieve near optimal regret without knowledge of any of the distributional parameters. Thank you.